Now that we understand electron shells and energy levels, the next important concept is electron configuration. Electron configuration is the systematic arrangement of electrons in the different energy levels or shells of an atom. In simple words, it tells us how the electrons of an atom are distributed among the K, L, M, N, and higher shells. Every atom has a unique electron configuration because each element has a different number of electrons. This arrangement is extremely important because it determines an element's chemical properties, its position in the periodic table, the types of chemical bonds it forms, and how it reacts with other elements. When scientists discovered atoms, they realized that electrons are not scattered randomly around the nucleus. Instead, electrons occupy specific energy levels according to well-defined rules. Nature always favors the arrangement with the lowest possible energy, which is the most stable arrangement. Therefore, electrons always occupy the lowest energy shells before moving to higher energy shells. This principle is called the Aufbau Principle, and it is one of the fundamental rules for writing electron configurations. The word Aufbau comes from the German language and means building up. According to the Aufbau Principle, electrons fill the available energy levels one by one, starting from the lowest energy level nearest the nucleus. The K shell fills first because it has the lowest energy. Once the K shell is full, electrons begin filling the L shell. After the L shell is filled, electrons enter the M shell, followed by the N shell and then the higher shells. This gradual filling of energy levels produces the electron configuration of every element. To understand electron configuration, we must first remember the maximum number of electrons each shell can hold. The K shell can hold a maximum of 2 electrons, the L shell can hold 8 electrons, the M shell can hold 18 electrons, and the N shell can hold 32 electrons. Although these are the maximum capacities, electrons do not always fill every shell completely before entering the next shell in larger atoms because the actual filling follows orbital energy levels. However, for the first 20 elements, the shell model shown in the illustration works very well and is widely used in introductory chemistry. Let us begin with the simplest element, hydrogen. Hydrogen has an atomic number of 1, meaning it contains 1 proton and 1 electron. Since the K shell is the lowest energy shell and has enough space, the single electron occupies the K shell. Therefore, the electron configuration of hydrogen is simply 1. The next element is helium, which has 2 electrons. The K shell can hold exactly 2 electrons, so both electrons occupy the K shell. Therefore, helium has the electron configuration 2. Since the K shell is completely filled, helium is very stable and belongs to the noble gases. Now consider lithium, which has 3 electrons. The first 2 electrons completely fill the K shell, but the K shell cannot hold any more electrons. Therefore, the third electron enters the L shell. The electron configuration of lithium is 2-2-1, meaning 2 electrons in the K shell and 1 electron in the L shell. Next comes carbon, which contains 6 electrons. The first 2 electrons occupy the K shell, leaving 4 electrons. These 4 electrons enter the L shell. Therefore, carbon has the electron configuration 2-4. These 4 outermost electrons explain why carbon can form 4 covalent bonds and is the basis of all organic compounds. Now let us examine oxygen, which has 8 electrons. 2 electrons occupy the K shell, while the remaining 6 occupy the L shell. Therefore, oxygen has the electron configuration 2-6. Since oxygen has 6 valence electrons, it needs only 2 more to complete its outermost shell. This explains why oxygen readily forms chemical bonds with many other elements. The next example is neon, which has 10 electrons. 2 electrons fill the K shell, and the remaining 8 completely fill the L shell. Therefore, the electron configuration of neon is 2-8. Because its outermost shell is completely filled, neon is highly stable and chemically inactive. This is why neon belongs to the noble gases and rarely reacts with other elements. Now consider sodium, which has 11 electrons. The first 2 electrons fill the K shell, the next 8 fill the L shell, and the remaining 1 enters the M shell. Therefore, the electron configuration of sodium is 2008-1. This single electron in the outermost shell explains why sodium is highly reactive. It can easily lose this electron to form a stable sodium ion, Na. Finally, let us look at calcium, which contains 20 electrons. 2 electrons occupy the K shell, 8 occupy the L shell, 8 occupy the M shell, and the remaining 2 occupy the N shell. Therefore, the electron configuration of calcium is 2008-2. Since calcium has 2 valence electrons, it usually loses both to form the Ca ion. The electron configuration of an atom provides valuable information about its valence electrons, which are the electrons present in the outermost shell. These are the electrons directly involved in chemical reactions and chemical bonding. Elements with the same number of valence electrons often have similar chemical properties. For example, lithium, sodium, and potassium each have 1 valence electron, so they belong to the same group in the periodic table and react in similar ways. Likewise, fluorine, chlorine, and bromine each have 7 valence electrons, making them highly reactive nonmetals. Electron configuration also explains why atoms form ions. Sodium has the configuration 2008-1. Losing 1 electron changes its configuration to 2-8, which is the stable configuration of neon. Therefore, sodium easily forms the Na ion. Chlorine has the configuration 2008-7. By gaining 1 electron, it becomes 2008, which is the stable configuration of argon. Therefore, chlorine forms the Cl ion. This tendency of atoms to achieve a full outermost shell is one of the driving forces behind chemical reactions. The illustration also introduces 2 additional quantum rules that become important in advanced chemistry. Hund's rule and the Pauli exclusion principle. Although beginners are not expected to master these rules immediately, it is helpful to understand their basic ideas. Hund's rule states that when electrons occupy orbitals of equal energy, they first occupy separate orbitals with parallel spins before pairing up. This arrangement minimizes electron repulsion and makes the atom more stable. The Pauli exclusion principle, proposed by Wolfgang Pauli, states that no 2 electrons in the same atom can have exactly the same set of 4 quantum numbers. In simple terms, this means that an orbital can hold a maximum of 2 electrons, and these 2 electrons must have opposite spins. Together with the Aufbau Principle, Hund's rule and the Pauli exclusion principle form the 3 fundamental rules used to determine electron configurations in modern atomic theory. Electron configuration is not just a way of arranging electrons, it explains many important chemical properties. It helps scientists predict how atoms react, the number of chemical bonds an atom can form, the shape of molecules, the electrical conductivity of materials, magnetic properties, ion formation, periodic trends, and the stability of atoms. Without electron configuration, understanding chemistry would be impossible. Electron configuration is also directly connected to the periodic table. The period number tells us the highest occupied energy level, while the group number for main group elements usually indicates the number of valence electrons. This is why elements in the same group have similar chemical behavior, they have similar outer electron configurations. A simple way to visualize electron configuration is to imagine a multi-story building. The nucleus is at the center, and the energy levels are like different floors. People always enter the lowest available floor first before moving to higher floors. Similarly, electrons always occupy the lowest energy shell first. Once one shell is filled according to its capacity, additional electrons move to the next shell. This orderly filling continues until all the electrons have been placed. So, Always remember these key points. Electron configuration is the arrangement of electrons in different energy levels or shells around the nucleus. Electrons always fill lower energy levels before higher energy levels. The K shell fills first, followed by the L, M, N, O, P, and Q shells. The Aufbau Principle explains the order in which electrons occupy energy levels. Hund's rule states that electrons occupy equal energy orbitals singly before pairing. The Pauli Exclusion Principle states that each orbital can contain a maximum of 2 electrons with opposite spins. The electrons in the outermost shell, called valence electrons, determine the chemical properties, bonding behavior, and reactivity of an element. Understanding electron configuration is one of the most important milestones in chemistry because it connects atomic structure with the periodic table, chemical bonding, ion formation, molecular structure, and virtually every chemical reaction studied in science. Once you master electron configuration, many advanced topics in chemistry become much easier to understand because the behavior of every element is ultimately governed by the arrangement of its electrons. After understanding electron configuration, the next important concept is valence electrons. Valence electrons are the electrons present in the outermost shell, also called the valence shell, of an atom. These electrons are the most important electrons because they are directly involved in chemical reactions, chemical bonding, and the formation of compounds. While the inner electrons remain close to the nucleus and usually do not participate in chemical reactions, the outermost electrons interact with other atoms. Therefore, when chemists study how elements react, they focus mainly on the valence electrons rather than all the electrons in the atom. To understand valence electrons, imagine an atom as a multi-story building. The nucleus is located at the center, and the electron shells are like different floors surrounding it. The electrons living on the topmost occupied floor are the valence electrons. These electrons are farthest from the nucleus and experience the weakest attraction from the positively charged protons. Because they are held less tightly, they can easily be lost, gained, or shared during chemical reactions. This is why valence electrons determine the chemical behavior of an element. Every neutral atom has a specific electron configuration, and the last number in the electron configuration always tells us the number of valence electrons for the main group elements. For example, sodium has the electron configuration 2008.1. The last number is 1, so sodium has 1 valence electron. Oxygen has the electron configuration 226. The last number is 6, so oxygen has 6 valence electrons. Carbon has the configuration 224, so it has 4 valence electrons. Neon has 228, meaning it has 8 valence electrons, giving it a completely filled outer shell. The illustration highlights sodium and oxygen because they are excellent examples of how valence electrons determine chemical behavior. Sodium has only 1 electron in its outermost shell. This single electron is relatively easy to remove because it is far from the nucleus and is weakly attracted. Therefore, sodium usually loses 1 electron during chemical reactions, forming the positively charged sodium ion Na. By losing this 1 electron, sodium achieves the stable electron configuration 2,8, which is the same as the noble gas neon. Oxygen behaves very differently. Oxygen has 6 valence electrons, which means it needs only 2 more electrons to complete its outermost shell with 8 electrons. Instead of losing 6 electrons, oxygen gains 2 electrons because that requires much less energy. As a result, oxygen forms the negatively charged oxide ion O. After gaining 2 electrons, oxygen also achieves the stable configuration 2,8, similar to the noble gas neon. This desire to obtain a stable outermost shell explains why atoms react with one another. Most atoms are chemically unstable if their outermost shell is not complete. They become more stable by gaining, losing, or sharing valence electrons. This tendency is often explained by the octet rule, which states that many atoms become stable when they have 8 electrons in their outermost shell, just like the noble gases. Although there are some exceptions, the octet rule successfully explains the behavior of many common elements. Valence electrons determine the reactivity of an element. Reactivity refers to how easily an element undergoes chemical reactions. Elements with only 1 or 2 valence electrons often lose them easily, making them highly reactive metals. Elements with 6 or 7 valence electrons tend to gain electrons easily, making them highly reactive nonmetals. In contrast, elements with a completely filled outermost shell are generally very stable and chemically unreactive. For example, the alkali metals, such as lithium, sodium, and potassium, each have 1 valence electron. Because they can easily lose this 1 electron, they are among the most reactive metals. Sodium reacts vigorously with water because it quickly loses its outermost electron to form a sodium ion. The halogens, such as fluorine, chlorine, bromine, and iodine, each have 7 valence electrons, since they need only 1 more electron to complete their outermost shell. They are highly reactive nonmetals. Chlorine readily gains 1 electron to form the chloride ion Cl, while fluorine gains 1 electron to form the fluoride ion F. The noble gases, including helium, neon, argon, krypton, xenon, and radon, already have complete outermost shells. Helium has 2 valence electrons because its first shell can hold only 2 electrons, while the other noble gases have 8 valence electrons. Because their outermost shells are already complete, they have little tendency to gain or lose electrons. As a result, they are chemically stable and rarely react with other elements. Valence electrons are also responsible for chemical bonding. Atoms form chemical bonds by using their valence electrons. There are 3 major types of chemical bonds. In ionic bonding, atoms transfer valence electrons from one atom to another. For example, sodium transfers its 1 valence electron to chlorine. Sodium becomes Na, chlorine becomes Cl, and the oppositely charged ions attract each other to form sodium chloride. In covalent bonding, atoms share valence electrons instead of transferring them. For example, 2 hydrogen atoms share electrons to form a hydrogen molecule, while oxygen shares electrons with hydrogen to form water. In metallic bonding, the valence electrons move freely among many metal atoms, forming a sea of electrons that gives metals their excellent electrical conductivity, thermal conductivity, and metallic shine. Valence electrons also help determine the group number of an element in the periodic table. For the main group elements, elements in the same vertical column have the same number of valence electrons. This is why they have similar chemical properties. For example, all group 1 elements have 1 valence electron, all group 2 elements have 2 valence electrons, all group 13 elements have 3. Group 14 has 4, group 15 has 5, group 16 has 6, group 17 has 7, and group 18 has 8, except helium, which has 2. This similarity in valence electrons explains why elements in the same group behave similarly. Lithium, sodium, and potassium all react vigorously with water because each has 1 valence electron. Fluorine, chlorine, bromine, and iodine all readily gain 1 electron because each has 7 valence electrons. Therefore, understanding valence electrons allows chemists to predict the chemical behavior of elements even before performing experiments. Valence electrons influence many physical and chemical properties of substances. They determine whether an element behaves as a metal, nonmetal, or metalloid. They affect electrical conductivity, melting point, boiling point, hardness, chemical reactivity, oxidation states, and the types of compounds an element forms. Nearly every chemical property of an element is connected in some way to its valence electrons. One of the easiest ways to determine the number of valence electrons is by writing the electron configuration. After writing the configuration, simply identify the outermost occupied shell and count the electrons present in that shell. For example, hydrogen, 1 valence electron sec1 helium, 2 valence electrons sec1 lithium, 2 1 valence electrons sec1 carbon, 2 4 valence electrons suc4 nitrogen, 2 5 valence electrons cuc5 oxygen, 2 6 valence electrons suc6 fluorine, 2007 valence electrons suc7 neon, 2008 valence electrons cuc8 sodium, 2008 1 valence electrons cuc1 calcium, 2008 2 valence electrons cuc2. As you can see, the last number in the electron configuration immediately tells us the number of valence electrons. A simple way to visualize valence electrons is to imagine the atom as a castle surrounded by several walls. The soldiers standing on the outermost wall are the first to meet visitors entering or leaving the castle. Similarly, the electrons in the outermost shell are the first to interact with other atoms. The electrons deep inside the atom remain protected and usually do not participate in chemical reactions. So always remember these important facts. Valence electrons are the electrons in the outermost shell of an atom. They determine an element's chemical reactivity and bonding behavior. Atoms gain, lose, or share valence electrons to become more stable. The last number in the electron configuration represents the number of valence electrons for main group elements. Elements in the same group of the periodic table have the same number of valence electrons and therefore have similar chemical properties. Valence electrons control the formation of ions, ionic bonds, covalent bonds, metallic bonds, and nearly all chemical reactions. Understanding valence electrons is one of the most important steps in chemistry because they connect atomic structure with the periodic table, chemical bonding, molecular formation, chemical reactions, and the behavior of every element. Once you understand valence electrons, it becomes much easier to predict how atoms will react, what compounds they will form, and why different elements exhibit such different chemical properties.